much. Thank you to Mr. Filimonov for the introduction and to the EPFL Student Association for Philosophy for the kind invitation. As it was announced already, I'm a philosopher. I work in philosophy of science today at the University of Geneva, but I was originally trained as a scientist, as a theoretical physicist, and I became known to my professors as a sort of a pain in the neck, because I would be the student who would always ask, well, why do we do it like this? Why do we calculate this and not that? Why do we start out from those assumptions and not from others? How do we know that these are the right sort of things to assume and this is the right way to proceed? So I naturally became a philosopher of science because that's exactly the kind of questions we ask. And it's the kind of intellectual endeavor which is, I think, a necessary accompaniment to the sciences themselves. So I'm not going to talk about ethics today, which is something that many people immediately associate, or that part of philosophy that many people would associate with the sciences immediately. They would recognize scientific research and the practice and the implications of scientific research may well have ethical implications, maybe also political implications. That is all very important, of course, but this is not the kind of philosophy I am working on. I work in theoretical philosophy. I'm trying to understand what is the nature of science. Is there such a thing as the one kind of thing that scientists do when they do science, and the one kind of method that they use to produce the one kind of knowledge that is supposedly superior to any other kind of knowledge? If we're in a time of a global pandemic, of course, science becomes, of course, relevant for society and politics, and it becomes important to consider and to reflect about why is it that we should believe the scientists and not those people who reject science for maybe good reasons, maybe for bad reasons. Is there anything in the way the scientific knowledge is generated that makes it superior knowledge as opposed to other ways? And what are legitimate kind of ways to question that primacy, that status, and what are not legitimate ways of questioning scientific knowledge? So, as I'm sure if you've read the newspapers, if you followed the media, many people question scientific knowledge, for instance, in virology in recent months and years. And some of the questions they asked are absolutely perfectly legitimate kind of questions that I think we should be, all of us, be asking ourselves, and others are not. And you who are future scientists and engineers, I take it, in the different sciences, natural sciences, mostly, I assume, I think it's important to get a little bit of that, I think, along the way. What is it that you're really doing? What is it to be doing science? And what, if anything, would justify the kind of activity that we do as scientists as hopefully leading to some sort of better knowledge than by mere guessing, by relying on mythology, on religion, on hearsay, on what you read in your social media, and so on and so forth. So this is the kind of question I'm interested in. And the kind of question I'm interested in then leads me to the question, what is it that scientists do when they do science? I mean, we need to understand, how is that kind of activity different from the kind of activity that would not be called science and that would not generate the kind of knowledge I'm interested in? So what do scientists do? At the most general level, I think, scientists identify some sort of phenomenon in the natural world, if they're natural scientists, in the social world, if they're social scientists, perhaps. And they try to understand that phenomenon. They try to explain that phenomenon. In order to explain a phenomenon, they may postulate laws of nature that are supposedly explaining why things happen the way they do. When I drop this object, why does it consistently fall down and not up, right? Well, because there is a law of nature, of gravity, and so on and so forth. Maybe these laws of nature are embedded in bigger theories, in Newton's theory of gravity, in general relativity, or in a quantum theory of gravity, or something like that. Sometimes scientists are not using laws or fully fledged theories. Sometimes they're just trying to identify causal connections. They start to understand if I change somehow, or if there is a change, whether I bring it about or not, change somehow in the input, how does that change the output? Is there a causal connection between the input and the output? So causal connection, causal networks, causal structures like this might be ways of explaining a phenomenon. And something that scientists often do in many sciences is they use models. They use models to explain some phenomenon. They use models, as we'll see, for all sorts of different purposes. So I'm going to offer to you tonight a sort of a reflection on what models are and on what roles models may have in science and in physics in particular. Because I'm a trained physicist, it's much easier for me to come up with examples in the physical sciences. I will have some other models for those of you who don't study physics. But I believe that many of the lessons that we will see are going to be perfectly generalizable to other sciences. I don't think that anything I say, or much that I say anyway, will be specific to physics, okay? And one lesson that I hope you will be taking away, that's, except that my computer now froze. Okay, there you go. So we ask, what are models in physics? And the thesis, I'm going to maybe not give you like a mathematical proof of, which is, you know, the sort of the highest possible standard perhaps of argument, but I'm going to illustrate it. Is the thesis that models in science in general and in physics in particular are a motley crew. As Americans would say, that term models refers to a very diverse and heterogeneous group of kinds of entities, of thingies, that's philosophy speak for thingies, which serve quite different goals in sciences, which makes it hard to give a sort of a unified account of what it is to be a scientific model and to have a unified one role that models play. In fact, in a way, this will illustrate the richness of science. I think it will illustrate or give us some evidence towards the conclusion that science is not one kind of thing that people do in one kind of way, following one method to produce one kind of knowledge. It's a much more heterogeneous sort of activity, which is very hard to somehow understand under one umbrella, which makes it the real challenge for philosophers of science to say, what is it that's somehow special to science, to all and any of the sciences, as opposed to the non-sciences? So this heterogeneity, as I already said, complicates giving a unified account of what models are in science and in physics. But conversely, if you look at the bright side, as you should, of course, is it gives a lot of opportunities to philosophers of science to study the various different ways in which science works. All right, now here are some ways models are used in physics. Sometimes when I was a student of physics, the physics professors would say, oh, it's just a model. Now, that has something dismissive about it, right? They're supposedly telling me I'm not really supposed to be thinking that this is how the world works. This is not how nature works. It's just a model. So this is sometimes said to invoke a cautious attitude where the referent, that is the thing we're talking about, that which is just a model, is supposedly a speculative, some sort of provisional account. Maybe it's incomplete, maybe it has some pedagogical value, but it's not the way physicists believe it's really the way nature works. Physicists often produce sort of tinker toy models, some sort of probing models. They say like, look, here's a phenomenon, we really don't know how it works, right? This is not just physicists, by the way. This is, you know, in the biomedical sciences, in the social sciences, scientists do this as well. They are faced with a possibly very complex phenomenon. So what they start is they play around with very simple models. They start to try and see, what if we make some basic assumptions and combine them and have some basic mechanisms that we postulate how this thing might work, and then see what happens, and then play around with it. It has something very playful this activity, like a child trying figuring different things out to understand how some sort, you know, maybe the remote control of the TV works, right? How do you do that? Well, trial and error, right? Give it different input and see what different outputs you might get, something like this. Then, of course, as I hope you know, people in Geneva get kicked out of the university if they don't know that, which, because it's been confirmed to a very significant degree at CERN in Geneva, the Centre Européen de la Recherche Nucléaire, is the standard model of particle physics. That's how it's called. So that's a model. So we've already, in like 3 bullet points, from the really most dismissive kind of attitude to the highest altitude of science, everything is called a model, even the very best of science, where physicists apply extremely high standards of statistical relevance of the phenomenon before they really declare that they have detected a particle. I forgot how much it is. I think it has to have at least 5 sigma relevance, which is an extremely high statistical relevance before the physicists would declare that they've made a discovery. Similarly, but much less well confirmed, is the so-called standard model of cosmology, which tells us that, you know, it all started with the Big Bang and then went through different phases of cosmic evolution until we basically have the universe as we can see it today, or as we believe it's structured today. So if you take a cosmology course, that's going to be the first semester, basically telling you what that standard account is with all the different periods and, you know, the physics that's relevant in each of these epochs. But of course, you know, scientists, they model other kind of phenomena. They model the atmosphere, the climate, the flow of a liquid in different kind of shaped containers, and so on and so forth. So there's a lot of modeling going on. Sometimes they speak of models when they mean some sort of solutions to a set of equations. So the Einstein's field equation is the core of general relativity. It's a complex kind of differential equation, really, and it has solutions. It's so complicated that unfortunately we cannot write down the most general solution analytically. But physicists have found some special solutions to that equation. For instance, Minkowski spacetime, which maybe you've heard about, is one solution to that equation, and it's called a model, therefore, of general relativity. Or we have mechanical models, for instance, of the solar system. I'm going to show you a picture of an orrery, which is a mechanical model of a solar system. and similar material devices. I'm sure in your high school chemistry lecture, you probably had some sort of models in the chemistry classes, which were supposedly showing you the structure of molecules with, I don't know, styrofoam pour foam and little, I don't know, iron bits or something to connect them or something like this, right? You can build up like models of a molecule, for instance. These are material models that are supposed to illustrate something, a structure of a molecule. Then there are so-called heuristic or non-representational models. So a non-representational model is a model that's not about something. It's not supposed to be illustrating something that really exists. It doesn't represent a thing. And you might ask yourself, what good is this? Why should we have non-representational models in science? And some of this is going to suggest a question which I would like to end, if there's going to be enough time, about the relation between models and theories. Okay, good. Now, by the way, if you have questions, don't hesitate to interrupt me and ask the questions. Either I could just go on and talk. I'm a philosopher. It's no problem for me to go on and talk for 90 minutes if I'm not interrupted. But I'm also happy to be interrupted because I'm here for you. So you should not hesitate to ask the questions you have. Okay. All right. So let's see what philosophers have done and how they've tried to characterize models, because we've now already seen a little bit a glint, sort of a suggestion that perhaps what it is to be a model is kind of a complicated, heterogeneous kind of thing. Here's Michael Weisberg, the American philosopher of science. But before that, we have a question. Yes?
Why heterogeneous?
Heterogeneous means very different kinds. So homogeneous is all of a soup with sort of a uniform structure and color and consistency and everything. And a heterogeneous soup is where you can see all the different ingredients still there. It's very, it's just not one kind of mix. So you have a very, very significant diversity of ways in which scientists call something a model, the very different purposes for which they use models, and so on and so forth. Okay, so Weisberg tried to bring some structure in that bewildering diversity and said, look, one could say that there's like three major kinds of models. And the first kind of models are concrete models. Concrete has nothing to do with the concrete you use to build houses. Well, I mean, that concrete is also concrete, but when philosophers say concrete, they mean as opposed to abstract. Concrete is something that you can touch or see or smell, or some material physical kind of thing. Okay, so it's a model like the high school chemistry model you had that you can touch and manipulate and do stuff with it. The second category are abstract models, mathematical models, models which you cannot touch or put on the table to show. Models for which I'm going to show you the examples in a minute. Which are abstract mathematical objects. And then the third category, which might sound like the second, but it's going to be different, and I hope to show you the way it's going to be different, are computational models. So what does this mean? What's the characterization generally? Concrete models, Weisberg says, are physical objects whose physical properties can potentially stand in representational relationship with real-world phenomena. So that's a whole mouthful of philosophers saying something. What does he say? They're physical objects. That means they're material things somehow. Now, these material things, they have physical properties like spatial relations, for instance, in the molecule model of your chemistry class in high school. There's spatial relations between the different colored balls that may represent different kind of atoms, for instance. And they stand in spatial relations with one or several connections between them, which represent the bonds, the molecular bonds between these atoms. So these physical objects have properties, and those are supposed to represent something in the real world phenomena. They may not be a perfect representation, of course, but they represent something that's salient, something that's important about the molecule, how a molecule is structured. That's why the chemistry teacher uses them, even though they're in many ways misleading, of course. They're not, this is not exactly how a molecule looks like. In a way, it's a very naive representation of a molecule. Nevertheless, it illustrates correctly some aspects that the chemistry teacher wants to highlight. Mathematical models, however, are abstract structures, like mathematical objects, like functions, like sets, like things like that. That they're not, you cannot touch them. They're not material. They're not physical objects. However, these mathematical abstract structures, they have properties which can now potentially stand in relations of mathematical representations of phenomena. So they are supposedly, nevertheless, representing something that's happening in the real world. So you have some magnitudes, some quantities in the world that are somehow supposed to be captured by the letters which go into an equation or a set of equations, of mathematical equations. Computational model, that's the final category, are sets of procedures. So they're neither abstract structures nor material objects, but they're procedural. You should think of them like an algorithm, right? This is what computation is. It's a procedural activity, in a way, of trying to compute something. And that's supposed to be a computational description of a behavior of some system. So you have a system that shows some behavior, and you try to compute that with your, emulate that in some way with your computational model. Okay, maybe some examples are going to help. So this here is the famous San Francisco Bay Delta model of the US Army Corps of Engineers who built this. So this is in a big hole in San Francisco or near San Francisco today. This in here is actual water. And this hole, I think, is I don't know, 60 or 80 meters long in total. So it's kind of a big material model. Here you see, this is the bay entrance. Maybe you can see this is the Golden Gate Bridge. I mean, it's not the Golden Gate Bridge. It's some wooden structure or something that they put there to signify this is supposedly representing the Golden Gate Bridge. That did they do that? Well, because in the 1950s, some people proposed that in that bay, which is all salt water, they built two big dams, one sort of cordoning off the northern part, which you don't fully see because it goes over here with the Sacramento River, and another dam somewhere here to sort of dam off the southern bit where you have the San Joaquin River getting in there. And the idea was that this would create gigantic freshwater reservoirs. Ooh. Huh. That's not good. Gigantic freshwater reservoirs, there we go, for the significant population that lives around San Francisco Bay. And that would have been great if it worked. So they built the model to see how these dams would change supposedly the fluxes of the waters and the tides. And when they tried to do this, so they had to do the hydrodynamics as realistically as possible to get an idea of how that would change the fluxes. And the problem was that they found was that, in fact, almost the entire ecosystem in the bay, consisting of all the marine animals and plants, would die off because they rely on the tides coming in from the ocean. So building 2 huge dams was a really, really bad idea for that. And so they didn't do that. But they did recognize that as a result of that model they built. That was not sort of previously known. Yes?
Can an experiment be conceived of as being a concrete model?
So you mean an experiment you build in a lab? Say when you do quantum optics, and you in your basement you have little lasers and mirrors and things like this. The problem there is, what exactly do you think you're representing? You're actually in an experiment, you're testing on the system itself, right? Namely, a light beam, for instance, and how the optics work. So I would say that's not really a model. It's the system you're interested in itself that you're testing. In a model, you don't normally use that target system, but you use some replacement, something else that's supposed to stand in for that real model, but is in the appropriate kind of relationship that you can nevertheless learn something about that system. So here, oh, okay. Okay, so in that model that the US Army Corps of Engineers built, that is not the real target system. What you're interested in, of course, is the actual bay and river deltas. But what you're doing is you try to make sure that in your model, the kinds of things you're interested in are faithfully representing what is out there. That's important, because if you don't have the water flows right here in the model, you're not going to learn what the dams are really going to do in the real thing. Okay, let me get this out of the way as well. Okay, here's another concrete model. That's the orrery I talked about. So this is an example from the mid-18th century, made by a British scientific instrument maker. That is already 250 years ago. That was a profession. So you could learn to be a scientific instrument builder, and that's maybe the kind of thing that you would then build. So this was a mechanical device that you can you can use sort of a curve like that and animate the thing, and then the machinery would actually turn around with the, I think this may be Earth, I'm not sure, this is probably the sun in the middle, I assume. So the planets would actually rotate around the sun at the relative speeds with which they do that, and including the moons. Here you can see there's I think this is a moon. Maybe this is a planet with 2 moons though, no? Or I'm not sure. Okay, but the moons around the planets and so forth and so forth. So this is also a concrete model. Here's an example of a mathematical model. That's the well-known Lotka-Volterra model, named after 2 mathematicians who formulated, it's really very simple mathematically speaking. These are 2 differential equations which are coupled. And what they give you is a predator-prey model of a population level phenomenon. So if you have rabbits and foxes, the more foxes you have, the less rabbit you tend to get, because the foxes eat the rabbits, which means the foxes will now die because there's not enough rabbits anymore to feed on. which means that the rabbit population can actually regenerate and grow again until it becomes so large that, of course, the fox population will now grow because there's abundant food, and on and on and on. So this is a sort of a negative feedback loop that you have with of a population level phenomenon. It's captured by these two mathematical equations. What exactly they say is not so important, but it's here P is the number of predators, foxes in my case, on H, the number of prey, the number of rabbits, for instance. And this is interesting because it shows a kind of dynamic that's actually applicable to many real world systems. It's a very general phenomenon of a negative feedback loop, expressed or captured by a mathematical model. A mathematical model in physics, for instance, could be, I mean, I hope you've seen an equation like that, even if you don't study physics. So that's Newton's law of universal gravitation, where the gravitational force is set equal to the product of the two masses of the planet and of the sun divided by the square of their distance, of their center of mass, multiplied by a proportionality constant, which is called Newton's constant of gravitation. Okay, I hope you've seen this. Now, this is the idea is that I'm giving you now a different kind of model from this here, but trying to capture the same thing. I'm trying to give you a model of how planets move around the sun, but a very different kind of approach. I do it in a mathematical way. And then I make an idealizing assumption, because otherwise, you know, if I have a 8-body problem or something like this, you know, even today, this cannot be computed analytically. And of course, in the day of Newton, they didn't have computers to do this numerically. So forget it. You have to make simple idealizing assumptions. And the one thing you do is you say the only relevant force is gravity. Forget about anything else. And in fact, I'm going to eliminate the gravitational interaction with other planets in the solar system, which is not insignificant, actually. That is a real thing. But it makes the computation much more complicated. So I say, if I want to calculate the trajectory of Venus around the sun, I'm going to forget about Earth and Mercury and Saturn and all the others. I'm really just going to look at the sun and Venus. And then I assume that both the sun and the planet are perfect spheres, which is not true, fully strictly speaking, but it's kind of an approximation. It's an idealization with some homogeneous mass distribution, so that the center of mass is exactly in the geometrical center of the body. That is also an idealizing assumption. And then I can therefore conclude that the mass of each object is assumed to be concentrated in its center. Basically, the sun and Venus are now point-like objects revolving around one another. In fact, I'm going to say, well, since the sun's mass is so much vaster than that of Venus, I assume that the sun is not going to move at all as a result of the motion of Venus, which is not true either, because Newton himself taught us that action implies an equal and opposite reaction. That's the third law of Newton's physics. So, of course, if there's a certain gravitational pull that the sun exerts on Venus, then Venus exerts exactly the same pull on the sun in the opposite direction. But of course, given that the mass of the sun is so much larger than that of Venus, the sun is not going to be moved much, literally, from that pull, whereas Venus, of course, is going to be pulled much more. Yes?
Or can we say that we place ourselves in the inertial frame of the sun?
Yes, you could do that as well, exactly. You could say, yeah, that's basically what we're doing. All right. So, and then we use Newton's second law. I hope you've seen this as well. F equals ma, the force or the acceleration of a body of mass m is given by the force that is exerted on it. Okay, and we say that this force is, of course, the gravitational force on that planet. So the acceleration on the planet Venus is going to be this force, which is given by equation 1 here. And we put this in. So I hope you don't have nightmarish sort of memories of high school mathematics when you had to do this. But I hope that's okay. So you equalize these two things. You can eliminate the mass of Venus, and there you go. You have a differential equation that can be solved now. We've made significant idealizations, but this has the virtue of being solvable. And basically, this is what Newton did. He solved this, and he showed using this that the planets move on elliptical orbits around the sun. From first principles, from general laws, right? So this is how a scientific explanation can work. So we have a model of planetary motion here that's mathematical, not honorary, not mechanical. Okay, so like many but not all mathematical models, this one is deeply grounded in deeper, more encompassing physical theory. So there's, you know, Newton wrote a very thick book about Newtonian physics, basically putting this on the ground. So I've just given you a very simple kind of model here in which all of this theory is in the background, as it were. Or we can actually do the same thing in using general relativity, even a sort of a more encompassing, more general theory, more fundamental theory. This is another example of the Ising model, which is a mathematical model of ferromagnetism in statistical physics, where you exemplify phase transitions. The interesting thing is, so you have a lattice of discrete variables here representing magnetic dipole moments of spins up or down, represented by these simple arrows. And then each of these atoms in that lattice, so each of these squares, interacts only locally with its neighbors, like here. The 4 neighbors like that, up, down, sort of north, south, west, and east neighbor, if you want. Okay. Now, this is pedagogically very useful. So those of you who took some physics course may have seen this before. But there's a real question whether it represents anything real in the world, whether any actual system, any actual real phase transition in a ferromagnet works like this. And that's the problem here is that the reality seems to be so much more messy that it's not clear whether this very simplified model represents anything. So you might ask your professor the next time they do this, well, how do we know this is not just a simple model that you like to teach us, but that it's actually, we're learning something about nature here? Did you have a question?
Yeah, because there is a phenomenon in physics known as universality that
Yes.
with that problem. It solves a bit that problem.
It's connected to that problem, yes, that's right. So you can have a sort of a universal kind of behavior shown by a large class of systems with underlying different materiality, if you want, but nevertheless show very similar behavior. This is why that model is supposedly very useful, because it's supposed to show some universal behavior, as you rightly point out. But whether it really does is a question. I'm not a physics lecturer, so we're not going to follow up this up. But that's the kind of question that you then, the kind of trade-offs that you face. You can have simplicity of a model versus explanatory power. So it should be as simple as possible, really, but not more than that, as it were. right? It shouldn't be too simple, because otherwise you lose what you're trying to explain. And that's sometimes sort of in the gray area where it's not clear whether you've crossed that border. So this is a computational model now. Moving to the last category, it's Schelling's model of segregation. Now, Schelling is an American, or was an American economist, and he had the following social phenomenon that he tried to explain. The social phenomenon was that in many American cities, you could observe segregation, meaning that the white people, people of European descendants, would be living in certain parts of town, whereas people of African descendants, for instance, would live in other parts of town, and Latinos yet in other parts. And there was relatively little mixture between the different racial groups. So that there was segregation. But he puzzled, he said, how can this be that in American cities, where we don't have race segregation laws, nevertheless, we observe segregation, just like in South African cities where you do have segregation. So in South Africa, you can explain this. You could say, why do the white people and the black people not live in the same neighborhoods? Well, because they're not allowed to. That would be an explanation, right? But how do you explain this in American cities where there are no such laws? That was Schelling's question. I want to understand why Black people and white people tend to live in the same neighborhoods without there being any such laws. And he came up with a very simple model, computational model. So he took a large piece of paper and he drew a very large grid like this. And then he took nickels and dimes. So I don't know whether you know what nickels and dimes are. They're 5 and 10 pence pieces, right, of American currency. One of them sort of silver colored and the other one more like copper, orangey kind of colored. And he would randomly distribute them on that grid. I'm using X's and O's. It doesn't matter so much, but not filling out all the little squares. Now you could say each X represents a person of one race. Each circle represents a person of another race. Now start with the random distribution, and I tell you the following rules, the computational algorithmic rules now. First of all, none of these people are racists in the sense that they absolutely don't want to live next to somebody who is of a different race. That's not the case. But everybody, the little circles and the X's, both of them don't like to be too crassly outnumbered. And he said, what if we assume, so for this cell here, you can define a neighborhood consisting of 8 cells around it like this, right? And you can apply the simple rule that anybody who lives in this square wants to have at least 2 people in the neighborhood who are of the same race. That's not racism. That's just, I don't want to be alone, with my color kind of attitude. And then you go through this computationally. You look at each of the cells. Is this condition satisfied or not? If it's satisfied, they stay put. If it's not satisfied, you take them out and you randomly use some sort of random procedure. You put them in an empty place randomly. And on you go. you have several computational rounds. This is an algorithmic model, right? And you realize what you will observe is that not always, but almost always, what you find is like big blocks, like neighborhoods, where the same kind of people start to accumulate. And then, of course, the more of the other race that move in, the more these people will be, the few remaining people will be moving out. So we have segregation, not because there are any laws, not because there's racism, just because nobody wants to be outnumbered, or at least not outnumbered crass. So this is Schelling's segregational model. By the way, this is a city map of Detroit. Blue represents African-American, red represents European American neighborhoods, and I think the orange here is the Latino parts, or maybe it's Asian, I'm not sure, I forgot. Okay, but something like this. Did you see how segregated this is? I hope you can see the colors. Yes?
It's just about the term you use. I don't think there is some race of people. Is it not better to speak about community or something like that?
So, okay, I don't want to make any politically incorrect sort of statements, but it's a sort of it's a naive simplification perhaps, but there are clearly people of African ancestry and of community of people of African descent, ancestry and of European ancestry and so forth, and individuals identifying with each of these communities, right? And so this is a simple model, probably not doing justice to the full sort of richness of the real problem. But this is very characteristic of model. You make a very simple kind of assumption, and it's certainly not going to be true that everybody has exactly the same kind of preferences. And of course, some people are going to be racist and so on and so forth. And some people don't identify with either of these groups and so on and so forth. So in reality, it's going to be much more complex than this. But nevertheless, the interest of a simple model like this can be a proof of principle that without there being overt racism, without there being segregational laws, nevertheless, you could have mechanisms of self-selection, basically each individual only deciding for themselves whether they want to move or not, nothing else, that could explain segregational patterns. That's the strength and interest of a model like that. Yes.
I was wondering if the scientific method, as it is an iterative way of testing hypotheses and trying to get further to the truth, could be considered as a kind of computational model for truth, to represent reality.
So the scientific method itself, ooh, that's a big question. So for me to know that, I would have to have a sense of the scientific method. And part of the problem that I'm trying to illustrate here for a philosopher of science is that it's really hard to find a unified one kind of method that scientists use when they do science. That's really the challenge here. In all this, and I'm just going to scratching the surface here of all the different kind of models that we have and scientific activity behind it, trying to somehow come up with scientific explanations of phenomena, of things we've observed either in the natural or in the social world, that it's going to be hard to be able to identify one kind of algorithm that's going to be the scientific method. I mean, maybe there is such a thing, but if there is, it's going to be something with a very, very complex algorithmic structure, I think, allowing for a lot of variety. Yes.
So now you're talking about the three types of model here.
Yes.
Where you can see with the definition of the model that there is some kind of evolution going on because the computational model would not exist 100 years ago. So of course there arises. So what is your lookout when technology drives new model creation? What is what you're looking for in the field before you're saying, okay, this might give rise to
yeah, that's an interesting question. So I think that the material, the concrete models, is something that's pretty old. So I think even in antiquity, there's some artifacts that we have found which can be interpreted as something like astronomical models, somehow representing some celestial phenomenon that was observed in antiquity. The mathematical models are certainly going to be much younger than that, but nevertheless, by the time of the scientific revolution in the 17th century or so, they are there. The mathematics in Newton, when you read Newton, doesn't look like quite the way I presented it. It's kind of a cleaned up version, but it's mathematical. There's no question about that. The computational, I think, I'm not sure, but I think I would agree with you that's something that arises later. Certainly in the 20th century, we have computational models. Not necessarily by using computers, because as I told you, this is using a sheet of paper and a pen to mark squares and you know, pennies and nickels or dimes and nickels, I think, and some sort of maybe die to roll to determine a random empty square or something like that. So it doesn't have to be implemented in a computer actually. But of course, today in science, most computational models are going to be some sort of computational program implemented in a computer. I mean, of course. I mean, it would be silly not to use that tremendous power, computational power, when you do computational models. So, but I'm not sure I can make any useful prediction of where this is going to go.
More as a philosopher, what are your lookout and you feel I can guess there is probably people that is having a certain area where they're trying to predict where is the new areas where there might be a complete new type of model you haven't seen before or defined before.
Yeah,
I'm
good. Yes. I'm sure that there are philosophers who would be very keen to discover something like that, like a new way of modeling something that does not fit any of the previous ways. I myself, I spend a lot of work. So I mostly work on the philosophical foundations, I would call, of quantum, or I would call this of quantum gravity. So that's theoretical physicists trying to bring together quantum physics on the one side and gravitational physics, relativistic physics, general relativity, in a fundamental theory that is a quantum theory of gravity that can explain the very early universe and black holes, which are both gravitational and quantum phenomena. And the problem there is one thing that we've relied on in pretty much all of science since the scientific revolution no longer works there. Any guess what that could be? I mean, yes.
Experiments.
Yeah, exactly. So in science, you know, when we do models like this, any kind of models or theories or postulate mechanisms or causal structures or what have you, we want to have this borne out in experiments, or at least in observations. Experiments is something where you actually manipulate the system to see how it reacts under different manipulations. Now, astronomers have a hard time to manipulate, you know, distant galaxies. So you have to, it's more observational than, strictly speaking, experiments. But nevertheless, it's empirical, right? You check, you see in the world whether or not your theories are borne out. And you better do that, because if what you're doing it is not borne out by experiments, then it doesn't seem to have anything to do with the world we're observing. I mean, that's the whole point, right? And now the problem is physicists are building theories in quantum gravity. I'm getting off topic here a little bit, but I hope this might nevertheless be of interest. Scientists, physicists are building new theories in quantum gravity based on different pieces of established physics that they believe are reliable pieces of physics, and that could probably be somehow extended into this new theory. But really, they have no guidance from experiments. The sort of stuff they do at CERNs, or the kind of things we observe with satellites or with telescopes, is way too low energy, way too late in the history of the cosmos, or is not close enough of the black hole to really see the kind of things you would need to see to experimentally test the theories of quantum gravity. And the question is, what is going on here? Is this still the sort of empirical method of scientific confirmation that we would normally demand? Or are there new standards at play when these physicists try to justify their theories? So that's the kind of question I'm very interested in. I don't think it's directly connected to modeling, but it's in a way connected to scientific method and whether maybe that scientific method evolves. So that is a very interesting question. Okay. Now here, I'm not going to click on this, but this is a computer simulation of the planetary orbits, giving you one other example of, again, the planet's motion. But I think you can find this yourself as a homework exercise. Google, computer simulation of planetary orbits, and you'll find many beautiful simulations where they have the different planets going around the sun. It's a computational model. It's algorithmic, right? It's some computer program code which tells your screen what to show. So it's a computational simulation of that motion. Did you have a question?
Do you believe in the gravitational quantum theory?
Whether I believe in them? No, I think they're all false. Now, what happens in quantum gravity is that all people of, the string theorists believe that all the other guys are false, but not they. The people in loop quantum gravity believe that string theory and all the other guys are wrong, but not they, and so on and so forth. But I mean, they don't really ultimately believe that. They're scientists. They know that, of course, they have to somehow live up to objective tests at the end of the day, and we don't know yet that. We're not there yet. But nevertheless, they are hugely, supremely confident in their theories, many of them. And that is a real puzzle for me. If you have no empirical confirmation of any of that, on what basis are you so confident in these theories? I mean, string theory extrapolates known principles of particle physics, for instance, but by many, 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 many orders of magnitude, by producing a theory that is extremely different from the standard model of particle physics. Why do you think that's still going to be a reliable extrapolation so many orders of magnitude away? We don't have
a religious paradigm that is created within the...
Yeah, so some not so well-meaning people have said this has nothing to do with empirical science. It's really more like mathematical theology. The question is whether this is nevertheless science. Presumably it is, because I mean institutionally it certainly is, because in physics departments you have people employed working in these theories. the Swiss National Science Foundation and any other national science foundation in other countries supports research in that. They publish in scientific journals and so on and so forth. So institutionally, they're definitely part of science. So the question is, what's going on really? That's an interesting question. Yes.
But you talk about the empirical thing, but Einstein, when he did the equation of the orbit of Mercury, then it was only explained with the telescope after like many years.
No.
No?
That's not true, no. So one thing that was known already from about the mid-19th century was that, so this is the sun, and this is my poor attempt at drawing an ellipse. Here, this is Mercury going around the sun. Something that was observed and known by the mid-19th century was that this is not, geometrically speaking, a closed elliptical orbit. What happens instead is that the perihelion, which is the point closest to the sun, moves around by a certain angle every year for every revolution. So Mercury, really what happens is it goes like this. I'm exaggerating now, but do you see what's going on, right? So it's not a closed form, it's something where the perihelion, the closest point to the sun, revolves with a certain angular speed every year. Now, so the Newtonians, what they tried to do is use Newtonian gravitational theory to calculate that angle. And what they found is about half of that angle. They just couldn't get the right value. So they postulated that there was another planet in here that would perturb, they called it Vulcan, perturb Mercury's path, and that might explain this. But they looked everywhere. There was no other planet in there. They could not find another planet. So this was a known anomaly of Newtonian physics. So it's not the case that this was only observed later. And Einstein, one of the very first things he did when he had general relativity in November 1915 was to calculate exactly this using general relativity, and was able to find a value which is extremely close, much closer to the observed value, to the known value, than what the Newtonians found. And Einstein himself was, as he said, I think, besides himself out of joy for days when he did that calculation, because he realized, oh, I might really be up to something here, onto something, I should say. Sometimes you're right. Sometimes, of course, you calculate something, you make a prediction based on a theory of something that's not yet observed. Either that or its absence. We just don't know yet. Of course that happens. And when that happens, what scientists do, they go to the experimentalists and they have a long conversation, and then they write the proposal to the Swiss National Science Foundation and say, hey, we should have such and such an experiment because our theories predict this and that, and we should check whether that's really the case or not. And then they do an experiment, and if they can, right? And that's the way science works. Sometimes there are known facts, observed facts beforehand that you then try to produce a theory, but sometimes it's also that you have a theory or a hypothesis for which you then try to deduce further consequences, for which you then don't make a retrodiction, as it were, sort of you predict backwards stuff that was already known, but instead you try to come up with novel predictions that was not observed yet, and then you try to build an apparatus that could do that. Now, maybe we're in that kind of mode when we do quantum gravity. Maybe we are formulating theories for which we would like to deduce some sort of prediction for which we can then apply to build bigger machines or something to test them. The problem is the quantum theories of gravity are not so well developed that we can really deduce very clearly numerical predictions for anything. And even if we did, the kind of energies that would be necessary are not something that is manageable even remotely by orders of magnitude with any of the technologies we have right now. So that's a sort of a real problem here. Okay. There's a computational model in physics of cloud formation. I mean, I'm not going to go through all of these examples, as I'm sure you can imagine, you know, in climate science, in meteorology, and so on and so forth. You have a lot of these models, sometimes very coarse-grained, sometimes very much interested in some detailed phenomenon like cloud formation. How do clouds form? So you need to know the chemistry of the atmosphere. You have a large number of equations, usually, that will give you the relative abundance of the different molecules and how they, how they're coupled to one another. As a result of this chemical, you know, how does the other chemical react, or of certain chemical reactions that you postulate of occurring in the atmosphere. You can then produce models based on largely understood atmospherical chemistry, how clouds can form, given, you know, the temperature, given the different altitudes, and so on and so forth. Okay. So some of these models are pedagogical, as the simple harmonic oscillator. If you've taken some physics course, I'm sure you've seen this, which can be both concrete, like a weight on a spring, which has a regular oscillation, or a pendulum, can be described to a good approximation as a simple harmonic oscillator, or of course a mathematical. That's why it's so pedagogical. You can do it in the first semester to physics students. You write down the equations and you can solve them, the differential equation for a simple harmonic oscillator. Then there's phenomenological models such as the MIT BAG model, which I'm probably not going to be able to tell you more about it, but it's models which are supposed to explain in a qualitative way, a bit like the segregation model, some phenomenon that you observe. So the MIT BAG model is a model that's used in particle physics to explain what's called quark confinement. So some elementary particles like protons and neutrons, for instance, are composite. They consist of 3 quarks. And it turns out that these quarks are confined in the particle, as it were. They cannot escape, really. That's the strong nuclear force that is explained by a theory called quantum chromodynamics, which is part of the standard model of particle physics. So I'm not going to give you a physics lecture here, but in order to illustrate that and understand that qualitatively, this simplistic phenomenological model was formulated, even though it is believed to completely mischaracterize what's really going on in a proton, say. There are heuristic models. So Bohr's model of the atom, for instance. Niels Bohr was a physicist who realized that classical physics is not going to be able to explain the constitution of atoms. So in the early 20th century, it was recognized that atoms are not homogeneous, unified thingies, but instead they have structure. There's a nucleus and there's electrons around it. It was not fully understood how it's possible, but is quickly people started to think of like the nucleus almost like the sun, and the electrons like orbiting around the nucleus almost like planets orbit the sun. The problem is if a charged electrons are charged, negatively charged, right? If they accelerate as they have to remain on a circular orbit, they have to accelerate, they will radiate away energy. So within actually almost no time whatsoever, they should really lose their energy, which is radiated away and fall into the nucleus. That's what classical physics, classical electrodynamics tells us about the atom. Now, Bohr realized, okay, that does not work. I mean, they're clearly stable, right? This is not happening. So how can we explain this? In classical physics, it seems to be impossible. So he came up with a model where he basically postulated that there must be orbits, and the electrons, they remain on those orbits, except when they occasionally radiate away some energy, in which case they kind of drop in the orbit, or if they absorb radiation, some energy, in which case they can jump up on a higher orbit, right? And he showed that by making these orbits the right kind and the right size, you can explain the numbers which were discovered by a Swiss high school teacher a little earlier by the name of Balmer, when there were events like this. Okay, anyway, that's a lot of physics again, but it's a heuristic model because Bohr realized I have no clue what is really going on. I'm just postulating this and it seems to capture something, but really quantum physics, atomic physics was not at all understood at that moment. So it could not have relied on the correct fundamental theory. It's very different from the Newtonian case where we have the theory and then use it to sort of model a simple system. It's a situation where we have no idea of the general theory and we make some observation of something and we sort of see how could this possibly work, right? And Bohr's model became famous because it gave us at least one way in which we could explain the stability of atoms. Okay, so if you take an advanced course in theoretical physics, you will come across a theoretical framework called quantum field theory, which is basically the sort of general framework in which the standard model of particle physics is formulated. And when you're taught this at the beginning, probably in like week 3 of the course or something like this, very early on, you will encounter a so-called phi-4 model, which is a pedagogical model for students to calculate, to do some calculations, because it's super simple and you can do some calculations, but it's really not supposed to be to correspond to any known physics whatsoever. There are no quantum fields like the ones you calculate there in that model, or at least as far as we know. Okay, I already talked about this. So what is the common core of what it is to be a model in all that kind of diversity? Yes.
How would you classify deep learning models in this framework?
So, sorry?
Will it be computational models?
I think so, yes. I think they're computational models.
Like in practice, computational just up to the point that you optimize some parameters, but then it's just like a statistical model, so mathematical. I mean, I don't know. It just.
Okay, I'm not sure I know enough about deep learning models, to be honest, to classify them. I would have thought they're computational models, but maybe I'm wrong. I invite you to correct me. Okay, yeah, it's a good question. So, you know, by the way, one important aspect here is also that there are some models which are not obviously only one of these things. Some of them may very much have aspects of two. For instance, Schelling's model here is a concrete model, right? Because it's paper, it's literally paper and pieces of money, right, that you use. So of course it's concrete, but it's also computational, because that was the point, right? To do some sort of simple computation, algorithmic, an implementation of that algorithm, really. So, I mean, maybe it's a better way to think that, you know, a model, any given model can fall under different categories and can have aspects of different ones, but maybe one of them is more salient than the other one, more important somehow. Because here, it doesn't seem to be so important, the materiality, right? That he took paper and coins. That was not really the important thing. We could have done this abstractly in a computer, you know, implemented in a computer, and maybe do in a number of other ways. It would still have been, in a way, the same model, right?
Isn't that also true of like these astronomical models where you build planets? In the end, you don't use gravity at all, either. So,
why do you not use gravity at all, you think?
To make a model of a solar system, which is completely mechanical.
Oh, a mechanical one, yes. Okay. Yeah, that's true. It's not gravitational. So it represents, however, a gravitational system. So it's a material body, a material object that represents some other material object in a very different way. Same here. This is material objects which represent, you know, supposedly real material cities and neighborhoods and so on and so forth. But here the salient point is that you have a computational procedure. You have an algorithm, and you can change the algorithm. You can say, what happens if instead of at least 2 of your neighbors are of the same group as you are, if you say that at least 3 have to be of the same, or only 1 has to be of the same group, and so on and so forth. And you can see how maybe differences in that algorithmic command is going to make maybe a difference to the patterns that you see arise. And maybe, you know, if everybody is satisfied with having just 1 neighbor of their own kind, then maybe not much is going to happen, and you will in general not see the emergence of segregation. But maybe it takes 2 or 3 or something, right? That's the sort of thing that you probe, and the materiality is then not so important. Whereas for the orrery, the material planetary system, the materiality is important, because it's the mechanical device that's supposedly showing you directly by direct perception how the different planets move in concert. Yeah. Yes, in the corner.
If you do an experiment to test some system and you put some data, you consider the data itself to be a model because it represents.
I consider the data.
You consider the data itself to be a model that you collect from doing an experiment.
Well, again, it represents something in the world.
A model or a certain part of it.
So what scientists sometimes do is they produce, or they look at what they call a data model. So they're trying to, for instance, to simulate an experimental situation, and they see what kind of data they would get, how you know, kind of modeling the data you would get under certain assumptions that you think are going to be implemented in the experiment. And then you have an effective data model, but I don't think that's what you're talking about. It's just any experiment, right?
So for instance, like say a system can exist in 2 states, right? And like your experiment is that, you know, if it's in 1 state, you get a 1, and another state you get a 0. You have a bunch of 1s and 0s. Maybe this is a mathematical model. If you like write it like on paper, then it's a physical model.
Right, because it's representing something, right? But maybe so in that sense, yes, it would satisfy that condition. But maybe now you start to sort of realize the trouble we got ourselves into in a way. We try to understand models in science and what scientists themselves call models, not what philosophers come and tell them they have to call models, right? That's scientists, their own use of words. But now we've come to such a general definition of what it is to be a model that you start to realize, well, you know, kind of it's so general that almost anything seems to fall under it, right? We just have some structure or some entities that represents some target system, something in the world. If that's everything it takes, you know, then I don't know, a map of the campus of EPFL will be a model. It is a model in a way, right? It's a material thing that represents a target system in the world, namely the real physical buildings here, you know, how they relate to one another spatially, right? But is that really what we want to say? Is it so general? So that's the problem. Anyway, there's another question here in the middle first, please.
Yes, can we consider that propositional logic is a model for the functioning of natural language?
So propositional logic is supposed to be representing some aspects of not just natural language, but of reasoning. It's not just the language, the structure of language, but it's of reasoning that we use in natural language, right? And it's supposed to capture something that's salient, but it's extremely a sort of a cleaned up version, right? Because in natural language is certainly a much richer phenomenon, and not all aspects of natural language are going to be captured by propositional logic or by predicate logic or any of the standard logic that logicians talk about. And on the other hand, it's not always, it's often not going to live up to the standards of logic, what we do in natural language, right? So it's a somewhat artificial representation of that. It's a cleaned version, right, of an aspect that we take to be particularly important, of course, in reasoning. But I mean, I don't think logicians call it the model of natural language. And I would be hesitant to call it of human reasoning, maybe, yes. Maybe it's however, more of a theory of human reasoning than a model. It's supposed to be a sort of even a prescriptive theory of human reasoning. This is how you ought to reason, following, you know, the rules of logic. Okay, there was a question in the background.
The common core of models.
Yes.
So I think that it means that basically it's something, a model that gives a better understanding of reality as it is. So it could be a practical understanding or a theoretical one, or that could be something else.
Mm-hmm.
Or even just understanding, just visualizing and being able to basically understand how things work.
Mm-hmm.
So for the 5-4 model.
Mm-hmm. The question is, what exactly do you understand when you understand that model? Because that model is not supposed to represent anything in the real world, the 5-4 model.
Yes, it shouldn't represent anything in the real world, but because you don't have the ability yourself to understand things that are not at your scale, it kind of makes you understand them better, even if another level can't. So to further your understanding of something that otherwise would not be, that otherwise would be out of reach.
Out of reach, you said. Okay. Yes, so it's like an enabler, maybe, right? Something that's like a stepping stone towards the real thing, so that you learn, you do your exercises, your finger exercises before you can play the real symphony, as it were, something like that. Okay, let me try to wrap up here because otherwise people are going to get impatient. But let me try to come at least to some sort of conclusion here. So Weisberg says, look, it's thinking again. At their core, all three types of models consist of an interpreted structure that can be used to represent a real or imagined phenomenon. So it's not always real. In the case of 5-4 or in some other cases, it's really sort of imagined. It's supposed to have a pedagogical value or something else. But there's a representation of something, of a phenomenon. They all these models have a structure. The Bay model is a concrete tub with a set of pumps and appurtenances. The Lotka-Volterra model is a set of points in a mathematically constructed space. The Schelling model is a set of states and transitions. So a state is one particular configuration of nickels and dimes on your cardboard, and then a transition is like when you transition from one state to the next, you update. You check for each one whether they're happy to stay there or whether they want to move. That's a transition. What makes these models of the San Francisco Bay, of populations of organisms, or of people in cities lies in the second part of the definition, in their interpretation. So they're interpreted to mean that, to refer to that, to represent that. Theorists have to intend a concrete tub to represent the San Francisco Bay, or the state transitions in a computational space to represent movements in the city. So when I take a dime from this position to that position, that's supposed to represent a person moving from one place to another. So these interpretations tell us what the model is about and set up the relations of denotation between models and their intended targets. So denotation is a fancy word for representing. So there are the things in the models and that which they're supposed to represent, their intended targets. Yes?
Can we consider numbers of letters or schematics as a model for representing reality?
Yes, of course. I mean, in general, this is absolutely possible. But as I hope from this quote becomes clear, there has to be a specific interpretation intended. That's part of what we do when we're modeling. So we may we may start out from a set of numbers or something like that, but we have to intend it to represent something that we want to model. Okay, so let me skip that. And here maybe, so this is another philosopher of science, a Swiss philosopher of science, who characterizes models as a simplified, or as referring to a simplified and stylized version of the so-called target system. So you have a target system like the solar system or the patterns of where people live in a city or what have you, and you simplify and you stylize away, because usually almost all natural phenomena and social phenomena are way too complicated to fully model. So you kind of simplify, you stylize, you clean up the thing, and then the part or aspect of the world that you're interested in, that's what the model refers to. Okay, so simply put, you can think of it that way. we have some structure. This structure can be concrete, it can be mathematical, it could be computational, it can have different characters or some sort of combination of these natures. But it's supposed to represent something that is the target system, the target phenomenon, something in the world. But as from some of your questions was already noted, that's an extremely general characterization now. That's really, we're getting to the point where this is too general to be useful, to understand something like the unified character of what it is to be a model. Okay, let me skip to the end. So models in physics, I hope to have shown you, or in science in general, are a motley crew. They're very diverse, a very heterogeneous group of things which have very different roles, very different levels of detail, very different ways in which they exist, very different kinds of structures. They serve rather different purposes. These purposes can be pedagogical, heuristic, meaning involved in the formulation or development of a theory. They can be exploratory, that is just, scientists playing around and seeing what happens if they do this or that. As I said before, and as I would like to emphasize again, a lot of science has this playful aspect of trying to figure out stuff. What happens if we do this, or if we try that, or if we add this or delete that, and so on and so forth. It may have explanatory purpose, computational, predictive. So sometimes we use models to predict something. So for instance, the weather forecasts we get from the Meteo, that's based on models, on computational models that are used to predict what the weather will be like tomorrow. They can be confirmatory. So we want to confirm theories, so we build models that can then, in one way or another, be observed to really explain something in the world, and therefore, or predict something, and by virtue of that being confirmatory, confirming the theoretical assumptions that were behind it when the model was built. Now, given this diversity, it's basically impossible to give a general characterization of what it is to model something or to have a model for something in science. Maybe that's disappointing news, but I don't see how, beyond the platitudes that I've shown you of a structure representing a target system, it's basically impossible to give a unified account that's supposed to capture everything that goes under the name of model in science. On the other hand, of course, as I hope you've seen illustrated a little bit, it gives us a lot of opportunities to think about what scientists are doing when they're doing these different kind of models. And because they're so varied and so rich, by studying all the different kinds of models that we find, we can learn a lot about many different aspects of science. So thank you very much. I think the time is more or less up, but if you have questions, I would be happy to answer them. Yes.
I have one. At the beginning of your presentation, you asked the question of why science would produce better knowledge of high quality than other methods. And after your presentation, I'm asking myself if we could say that science is what characterizes science is the aggregation of different kinds of models that are coherent with one another. So we use one to explain these things, and when it becomes too big, we use, okay, we now use another model to bridge with the another thing which is way larger. And when I mean coherent, is that
they can be linked together.
Right. No, I think that's an extremely interesting thought. And I think in science, that is a very central aspect of scientific activity. And it doesn't just concern models, but in science, whether we're looking at entire theories or in models or in other aspects of explanations or mechanisms or something, they have to cohere. They have to somehow match. And if we look at the intersection of two things, we have to be able to control that too, eventually, right? So for instance, you know, if you have a chemistry, you have anorganic chemistry, and some understanding of what that's supposed to work and some sort of theories about that, or maybe models of how, you know, of anorganic chemistry. And then you have some physical theory that tells us something about the constitution of matter, the structure of atoms. They have to cohere at the end of the day. We have to bring together our understanding of how molecules are built and the structure of molecules with the way atoms are constituted. If we cannot make them coherent, there's a big problem there for science, right? And science often works like that. You bring together different strands depending on what exactly you're interested in, and at the end of the day, they all have to cohere. Now, I think this is not quite sufficient, though, because, for instance, it's not so popular today, but for a very long time in the history of ideas, at least in the Western world, religion played an extremely important influence. And there was in the Christian tradition a very long-standing, elaborate tradition of producing an explanation of much of the world as well. Maybe not so much the natural phenomena, but the social order, for instance, and sort of what's behind all of this in a way. A philosopher will call the metaphysical aspect, those which go beyond the merely physical ones. Now, that provided a very powerful and detailed paradigm of explaining much of what was going on in the world. And it was extremely coherent. There were scholars in medieval times, many of them, whose basic job was to form a coherent whole by taking passages from the Bible, and if there is an apparent conflict between different textual passages from the Bible, you have to produce an account that makes them cohere. You have to give a sort of a theological metaphysics that can provide an overarching Christian worldview. And this was done with a lot of intellectual energy, with a lot of manpower invested in that, an extremely coherent picture. And yet, today, many of us believe that this is not the right way to understand natural and social phenomena. So it's, I mean, regardless of which one is better, but clearly if we want to say A is better than B or B is better than one, it cannot just be coherence. That's a sufficient condition. It has to be something more than that.
And you're saying that there is a similar pattern between the explanation of the world by religious theories and by physical theories. That means that
it's a, yeah, sorry.
Yeah, the goal is to justify everything to be coherent between one another. One uses the Bible as a basis, and the others maybe experiments and mathematics and
yes. So I certainly think the goal is not completely different. I wouldn't say it's identical. So I think in the Christian paradigm, the goal is not just to explain the phenomena of the world, but to also give and justify a moral order, right? And science, I think, doesn't have that goal. Science has the goal of explaining natural and social phenomena. That's,
what about the law of economics?
yes, that's a social order. You're right. That's maybe a social phenomena. Look, I mean, this is what philosophers of science do. I think I'm getting a sign that we should wrap up, right?
Kind of, maybe a few last questions, but yeah.
Yes. No, that's fine. So when you, as a philosopher of science, you're interested in trying to see first whether there is something that makes science unique, cognitively speaking, in terms of, you know, knowledge as a knowledge producing activity in any way unique against all other traditions, including religion or anything else. Is that the case? Is it unique? And if you want to argue that it's unique, you better have a reason to say why and on what basis such uniqueness can be justified. What makes it a systematically better approach to generating knowledge about the natural and social world, for instance, than any other approach? And the trouble is when you're you will want to say, yes, it is better. When you go and become you're a member of the task force advising the federal council what they should do or not, and what the science tells us about the virus, and so on and so forth, you better have some reason to think that what the kind of knowledge that science has produced is systematically better than other ways of trying to explain, the symptoms, as it were, in individuals and in the society, that, you know, some sort of conspiracy theories or something like that, right? Now, if that's not the case, then we're in trouble. How could we justify all the things we're doing if that's not the case? So there better be some difference. But when you think about it, it's not so obvious what that difference is. There's not like the one magic key that you can have and say, if you satisfy this criterion, then you're science, and then all is good. It doesn't work like that. Science is not something that can be captured on one slide with one method, with one characterization, one condition, which is somehow a necessary and sufficient condition for what science is and what science does. It's a huge challenge. It's an interesting challenge, I think, but it's something that I think most philosophers of science accept today, that science is a much more heterogeneous, diverse, rich activity, which has many, many, many different aspects, which overall seem to lead to remarkably impressive results we couldn't have dreamt of 100 years ago or so. But on the other hand, is so rich and diverse, and that it's hard to sort of identify the scientific method. That's both the interesting and the challenge of philosophy of science. Yes.
Well, I don't understand, because you said that basically there was nothing. Well, the differences in science and things like that aren't really scientific. Difference isn't really there, or is?
No. That was in response to his question when he said that, you know, it's about the coherence of the models, whether we couldn't characterize science through that. And I doubted that was going to uniquely identify science. There are other activities which may be highly coherent in themselves, but not be scientific.
Isn't science at its core, so in the beginning at least, question of reproducibility?
Of reproducibility, or? Yes, no, that's certainly an extremely important idea. So I think overall, the answer will have to do something with the idea that we have empirical means, a whole arsenal of empirical means of testing and confirming or disconfirming a scientific theory by empirical means. And there's a number of rules we have to follow to live up to scientific practice. One of them is that we would like to see certain observations to be reproducible in similar but distinct circumstances, for instance. That is, if a different lab in Zurich builds the same kind of apparatus, they should see the same thing we see here in Lausanne. Otherwise, there's a problem. We cannot really say we've confirmed it, right? So yes, of course, there are many rules like that. But it's not like, as I said, one slide I could tell you this is what science is and that's it. This is why you have to study for many years, I guess, to become scientists.
Can we just take one last question, because afterwards we would like to invite you to eat, and so the restaurant is going to close.
Okay, yes, sure. Okay, last question.
Yeah, I heard a bit about the Tarski model theory, where as far as I understand it, the truth is defined as a correspondence between a structure displayed by a and the wall. And it's now outdated in epistemology, or it's still an important framework.
Oh, I see. So that's a huge other topic. Yes, the problem of truth. What is truth? And you're quite right to say that the simple model in epistemology of truth as direct correspondence between propositions, say, and facts that obtain in the world or something like that is problematic. But I'm not an expert on truth. I hope that it exists, but other than that, I'm not an expert. So.